In this lesson, we're going to review electron configurations. To quickly review before we get started, I want you to think about what valence electrons are. Valence electrons are the ones that do the interacting with other atoms. That is what makes chemical reactions and chemical bonding occur. They are the outermost electrons of an atom. So if you think back to the Bohr diagrams that you drew or modeled, where you had rings around the nucleus and your electrons were floating around on these rings, the electrons that are in the outermost ring there, an outermost shell, so something like this guy and this guy, they would be your valence electrons. And remember that the periodic table can help you determine the number of valence electrons that an atom has. So I know this is the first slide, but I'm going to label this periodic table. This column, the hydrogen family, these have one valence electron. Helium has two, so this is why it's drawn over here. Helium, but beryllium and down, they have two valence electrons. Skip across the middle for now. Boron and family 3, carbon 4, nitrogen 5, 6, 7, 8, except for helium. Helium only has 2. Alright, so the first thing that we did in this unit was to draw electron dot diagrams. So when you're asked to draw an electron dot diagram, the first thing you got to do is figure out what atom you're working with. So if I ask you to draw the electron dot diagram of nitrogen, let's say, you have to not only figure out what atom you're working with, but tell me the number of valence electrons. Well, if we go back to this first slide, nitrogen has 5 valence electrons. So how I represent that is write the atomic symbol or the element symbol and then draw circles around that to represent each valence electron. And you'll never have more than 2 on one side. And if you can remember the videos that we watched, the rules are that you put 1 electron on each side of the atom or the elemental symbol before you buddy up. So this would be the electron dot diagram for a nitrogen atom because there are 5 valence electrons. You only draw the valence electrons. Nitrogen actually has 7 total electrons, but only 5 valence electrons. Alright, here are some more examples. Phosphorus has 5, it's also in the nitrogen family. Carbon has 4, chlorine is a halogen, so it and the rest of its family have 7, and oxygen has 6. You'll notice that with oxygen, we didn't draw both electrons on this, both of the unpaired electrons here on one side, because your rule, remember, is to draw 1 on each side before buddying up, which leaves on oxygen 2 unpaired electrons. Helium, again, is the exception. Based on where it's at in the periodic table, you would expect it to have 8 valence electrons because it's a noble gas. However, when you only have 2 electrons total, you can't suddenly have 8 valence electrons. Both of helium's electrons are in the very first 1s orbital, which only holds 2, which means that helium only has 2 valence electrons. Orbital diagrams now. The rings around an atom's nucleus, so back to that Bohr diagram that we were talking about. These spots where electrons can be found are called energy levels. So each ring or energy level has a limited number of parking spots for electrons. So each one can only hold so many. It's like when you're in a parking garage. You can't park in a parking garage where there's no space for you to park. So if you're on the bottom floor and there's no empty spaces, you go to the next floor. And that's exactly what electrons do. If there's no room for it in an energy level, it goes up to the next energy level. The periodic table can help us determine the number of energy levels around our nucleus. Just as how we determine the valence electrons by columns, the row can tell us how many energy levels surround the nucleus. So for example, if we look at this little chunk of the periodic table, this is the first row, row 1. So it has 1 energy level. This has 2 energy levels, 3, 4, 5, and so on. So if I ask how many energy levels surround a magnesium atom, you would just look at the row number and tell me that it has 3 energy levels. And that goes for any element on the periodic table. So an orbital is a place where electrons can be found. When you have an energy level, there's certain spots, as we said, the parking spots that are available. Well, these electrons are constantly moving, so really when we say that it's floating around in an orbital and it's spinning a certain direction, that just means it's had a high probability of being there. Like, we don't know exactly where it is, but we have a pretty good idea. So the shapes, or the paths that these electrons could possibly take while they're in this orbital, or while they're in this energy level, are called orbitals. So they have different shapes and different energies. This is a diagram representing the types of orbitals that we've talked about. So an s orbital has that sphere shape, p orbital has the dumbbell shape, d orbital the clover, and the f orbital the cluster. So the three orbitals that we focused on in class were the s, p, and d orbitals. Orbitals can hold a different number of parking spots, or a different number of electrons, based on the number of parking spots it has. So the places that are the parking spots, or the homes for electrons that exist in each orbital of each energy level, are called subshells. So you can think of subshells as being the level in a parking garage. Each subshell, which we draw with a line, can only hold 2 electrons. And we use arrows or half arrows to show electrons in their parking spots in the subshells. But before we can do that, we've got to remember that electrons are constantly spinning away from each other because, like charges repel. So because both are negative, we represent 2 electrons in the same subshell as spinning in opposite directions. One spinning up, one spinning down. Differently shaped orbitals have different numbers of subshells, so different amounts of lines that we could draw to place electrons in. The s orbital only has 1 subshell that can hold 2 electrons. The p orbital can hold 6 electrons total, or at most, because it has 3 subshells and 2 can go in each. The d orbital has 5 subshells, which can hold 2 electrons each for a total of 10 electrons total. And if these were full, the orbital diagrams would look something of the sort. Different energy levels have different orbitals. Any electron that is in the first energy level, so the first row of periodic table, those elements have electrons in the first energy level, as do every other element, they must be found only in an s orbital. So if a valence electron is found in the first energy level, the only spot for it is either it's spinning up in the 1s or spinning down in the 1s. Electrons in the second energy level could either be in an s orbital, which again is the line, or a p orbital, which means they're in the second energy level you can fit 8 total electrons because you've got the 2s and the 2p. So you can fit a total of 8. There's 8 possible parking spots you could have on the second floor, if you will, or second energy level. And 3rd through 5, they have an s, a p, and a d. So they can hold a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 17, 18. So periods 3 through 5, or energy levels 3 through 5, can hold a total of 18 electrons total. So again, the first energy level holds 2 electrons total, 8 in the second, 18 in 3rd through 5, or 3 through 5 energy levels. So what does this mean? Every time that you write or you label orbitals, you will always follow this order. In the first energy level, if you arrange them by increasing energy levels, in the first energy level, only an s orbital, we call it an s subshell, we call it the 1s orbital. In the second energy level, we've got the 2s and a 2p, and 3, 4, and 5, we've got sp and d. Orbital notation corresponds to when you are drawing a diagram. So when you draw these lines and you put arrows in them, you can write the orbital notation or draw an orbital diagram for any element on the periodic table. Now, there is a certain order to filling the parking spots for the electrons. So you need to be the cop that directs traffic. You can follow this order along on the periodic table. This order, 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, you need to know and become very familiar with if you're not already. One way that you can help remember the order is by drawing an arrow diagram. Some of you might have seen this if you watch some videos online. It's not something that I spend a whole lot of time talking about in class, but it has proven to help some people. If you can remember that the s orbital, or the one energy level has an s orbital, the 2 has s and p, 3 has sp and d, 4 sp and d, and 5 sp and d. The way that you can remember, or at least draw this every time you take a test or an exam, is by starting on each energy level. Go from, in your first available place to park your electrons, go from top right to the left edge. This is the first spot you would put electrons. If you fill that, go to the next row, first place to put them, top right, bottom left. You would fill the 2s next. The next time you would go 2p, 3s. Then 3p, 4s. Then 3d, 4p, 5s. Then 4d, 5p. This would help reinforce the fact that 3d would come after the 4s orbital if you're parking electrons. Alright, so let's do a couple examples. Hydrogen has 1 electron. The only place it could ever go is in the first energy level, in the s orbital. So I'm going to draw it with an up arrow. Helium has 2 electrons. Well, they both go in the 1s orbital as well. Just as the pigs in the Hog Hotel would rather partner up with someone than climb a floor to the next energy level, they share the parking spot. Lithium, now 3 electrons. Well, the first 2 we know go there, but now we've got 1 left. Well, the next energy spot for the electron to go would be the 2s orbital. So this completes our orbital diagram for lithium. Carbon. Carbon has 6 electrons. Well, the first 2 go here, then 2 more, so now that's 4 total. But now, when we reach a p orbital, so for p and d orbitals, the rule that we went over with the Hog Hotel, where a pig or a hog would rather have his or her own room than buddy up if it's possible, applies for the p and d orbitals. So this is where you would put 1 in each room, or in each subshell, before partnering up. So for carbon, we have 2 electrons left because we've got 2, 4, and I have 2 more to put in. So they would not be in the same room together. The rules that we had to follow, or the principles that we had to become familiar with when talking about electrons and the placements and electron configuration, are the Aufbau principle, Hund's rule, and the Pauli exclusion principle. The quickest and easiest one to remember is that if you draw a line to represent a subshell or an orbital, you can't have any more than 2 electrons in it. So it's just like with the Hog Hotel, you could only have 2 pigs to a room because they were so smelly. So 2 electrons max per orbital. So per line that you draw, don't ever put more than 2 arrows in it. The Aufbau principle says, alright, if the options are to fill in the 1s or the 5b, your electrons would rather go to a lower energy level, just like the hogs would rather go to a room on the first floor of the hotel than climb stairs to the next one. If you have multiple orbitals or subshells in an energy level, they all have the same level, or they're all of equal energy. So, for example, the 3p orbital with the 3 subshells, neither one of these has greater energy than another, but still the rule applies that they'd rather be by themselves before they would buddy up. Lastly, Hund's rule says that if you've got 2 electrons in the same subshell or in the same orbital, they've got to be spinning away from each other because like charges repel. So remember when we did the Hog Hotel, you had to put 1 hog facing up and one hog facing down, the electrons, one must spin up and one must spin down. Now, to write electron configuration, if you remember how we drew the orbital diagram for carbon with 6 electrons, you can, from this, write what we call the electron configuration. So, electron configuration is just a shorthanded way to write all of this. So instead of drawing out the arrows every single time, you could just tell me the electron configuration, and that would be enough. Now, how to go from the orbital diagram to electron configuration is that you write the names of the orbitals that you have electrons in. It doesn't matter if they're full, but you need to tell me what orbitals you have electrons in. So I know I've got arrows drawn in the 1s orbital. I also have electrons drawn in the 2s orbital, and my last 2 electrons are in the 2p orbital. Now what you do is tell me how many electrons you have in each one of these orbitals. The way that you demonstrate how many electrons you have is by putting a little number up at the top here called a superscript. So in the first orbital, in the 1s, I've got 2 electrons. In the 2s, I've got 2, and in the 2p, I've got 2. So my electron configuration for carbon is 1s2, 2s2, 2p6. Let's draw the orbital notation and talk about the electron configuration of krypton, which has 36 electrons. So the first 2 would go in 1s, and if you want to remember your order, you might want to draw this off to the side. So we would fill the 1s first, then the 2s, then the 2p, then the 3s. So 2, 3, 4, 5, 6. So far I have 10 electrons. You might want to keep track. 11, 12, 13, 14, 15, 16. And I'm already demonstrating bad habits. Put 1 in each before you double up. So I've got 18 total, 19, 20 because I fill the 4s before the 3D, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. So I followed my orders, in my order of filling the orbitals, and I am left with this orbital diagram of krypton. Well, now, the way that we write the electron configuration, if you remember, is by naming the orbitals that you have electrons in. So I have electrons in the 1s orbital, in the 2s, in the 2p, in the 3s, in the 3p, the 4s, keep that order the same, the 3d, and the 4p. Now I add superscripts to tell me how many electrons I have in each. I've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. A trick to remember for noble gases like krypton is that besides helium, every single one of the noble gases will end in some number p6. Iodine. This one has quite a few electrons. 53. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53. So now the electron configuration, I've got electrons in the 1s orbital, the 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p. Now I've got 2, 2, 6, 2, 6, 2, 10, 6, 2, 10, 5. So my electron configuration for iodine is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p5. Now, lastly, I want to talk about noble gas notation. Well, we already know that electron configuration is a shorthanded way to write all those arrows that we've got drawn on those lines. Well, there's an even shorter way to describe how the electrons, or where they're at in placement-wise or orientation around the nucleus. Noble gases, we know they have a stable electron configuration. I just talked about how they all end in something p6, depending on what row they're in the periodic table or what energy level their electrons are in. They have what every atom wants, a full outer shell, 8 valence electrons. So how you can use this to your advantage, or to perhaps expedite the process of writing electron configuration, is to do this shorthand notation. All that noble gas notation is telling you where the electrons are beyond the electrons that already would fill up a spot of a noble gas. So when you're doing this, your job is to find where your element is on the periodic table. So let's say sodium, which is element number 11. It is in row number 3. Well, now we got to go back to the last noble gas that you would pass if you increase from atomic number from 1 to 11. Well, the last noble gas that we pass would be atomic number 10, which is neon. So neon is the last noble gas as you increase in atomic number. So the noble gas, the element all the way to the right of the periodic table, in the row above that of sodium. So when you do this, if you were telling me the electron configuration of sodium, you could say, all right, well, I know it's just like neon, and you say that by writing the symbol for the noble gas in brackets, and then I have 1 electron beyond the electron placements in neon, because neon has 10 electrons, sodium has 11, and I know sodium is in the third energy, sodium's valence electrons are in the third energy level, so I would have 3s1. Because neon's electron configuration is 1s2, 2s2, 2p6. Well, sodium's is 1s2, 2s2, 2p6, 3s1. So what this is saying is that, okay, where these are the same, you can just write neon instead. And then what's beyond it. So, for example, let's do bromine. Well, as you move across the periodic table of increasing atomic number, the last noble gas that you pass is argon, because bromine's atomic number is 35, and the last noble gas you pass is element number 18, which is argon. So again, if you were to draw the electron configuration or write the electron configuration for argon, it would be 1s2, 2s2, 2p6, 3s2, 3p6. Now, as you start off filling in those first 18 electrons for bromine, you would see the same stuff appearing right here. So a way that to save some time, you can just say, okay, argon, and tell me what are the electrons beyond that, which if you look at the periodic table and follow along with your orbital diagram filling in, you would see that the remaining 17 electrons would be 4s2, 3d10, 4p5. So let's do another example. Writing the noble gas notation of indium, element number 49. The last noble gas before that is krypton. So beyond krypton's electrons, beyond the 36 that krypton has, I have 13 more I need to place, because krypton has 36, 49 minus 36 is 13. So I have 13 electrons that have to go somewhere past where the electrons of krypton would go. So krypton ends with an electron configuration of 4p6, which means my next place to go is 5s, then 4d, then 5p. Well, I have to fill 13 electrons. 2 go in the 5s, because it's an s orbital, it can only ever hold 2. In the 4d, that can hold 10, so 10 go there. And the last of the 13 needs to go in the 5p orbital. So the noble gas notation for this element is the noble gas of krypton, 5s2, 4d10, 5p1. Go ahead and practice these, writing the noble gas formations, so that you can learn how to read noble gas notation and go back to find out what element it is. Also, to get practice writing with electron configurations. And remember that every time you write an electron configuration, every single one of these superscripts should add up to not only the number of arrows that you have, but also the atomic number or the number of electrons in an atom. So if this was with this being for iodine, the square on the periodic table for iodine shows something like 127 in the bottom for the atomic mass, and then 53 in the top for its atomic number. So when you look at the periodic table, this number, the whole number at the top, tells you how many electrons this atom has. So you should have exactly that many arrows and exactly that sum when you add up all of the superscripts.